The research proposes the utility of an existing metric, deviation from stochasticity, DS, measure to characterize resting state fMRI time series for Alzheimer's disease, AD, classification. The DS measure quantifies the lack or presence of structure in a signal, which can lead to discrimination between healthy and AD subjects. An autoencoder-based model is used to learn efficient representations of fMRI time series data. The methodology is applied on fMRI time series of 50 healthy individuals and 50 subjects with AD, obtained from the ADNI database. The study aims to create an efficient diagnostic technique for AD classification by analyzing the structural disparities in fMRI time series of the default mode network, DMN. The DS measure is applied to identify significant differences in the level of structure between healthy and AD subjects, achieving a peak classification accuracy of 95% using a gradient boosting classifier. This approach has the potential to provide a novel biomarker for AD classification, leveraging the strengths of fMRI and machine learning techniques. The research focuses on diagnosing Alzheimer's disease, AD, using the deviation from stochasticity, DS, measure in resting state functional magnetic resonance imaging, RS-fMRI, data. The approach involves analyzing the brain's default mode network, DMN, for significant changes or varying patterns that contribute to disease classification. The study utilizes a novel method to quantify the deviation from stochasticity in RS-fMRI time series, aiming to classify subjects into healthy and AD-affected groups based on the DS metric. The methodology includes loading and preprocessing of fMRI data from the Alzheimer's Disease Neuroimaging Initiative, ADNI, database, focusing on the DMN regions. The DS measure is applied to identify the deviation from stochastic behavior in the time series of brain regions, allowing for the classification of subjects and the identification of significant regions of interest contributing to the disease. The proposed method is designed to overcome the limitations of existing techniques by providing a more accurate and robust classification approach. Motion correction. Correcting for subject motion during the scan by aligning each volume to a reference volume or by estimating and correcting motion parameters. Artifact removal. Addressing additional artifacts such as physiological noise, e.g., cardiac and respiratory fluctuations, using techniques like physiological noise regression. Intensity normalization. Adjusting voxel intensities to correct for variations in signal intensity that can occur due to scanner differences or subject-specific factors. Smoothing. Applying spatial smoothing to the data to improve the signal-to-noise ratio and facilitate statistical analysis. Registering fMRI to MNI template. Performing spatial normalization to align individual brain images with a standardized anatomical space, the Montreal Neurological Institute, MNI, template. This process involves several steps to achieve spatial normalization, including preprocessing to correct for distortions and ensure uniformity across the dataset, co-registering fMRI data to the high-resolution structural image or the MNI template, and applying nonlinear transformations to map each subject's brain into the MNI template space. Plotting the DMN with several ROIs. Using a parcellation scheme that covers various cortical and subcortical areas of the brain, the Dozenbach Atlas, derived from resting state fMRI data, to divide the brain into 160 regions of interest, ROIs, based on functional connectivity patterns. The default mode network, DMN, refers to the parts of the brain that are more active when at rest. It represents brain activity when not engaged in a particular cognitive task, and the brain areas within this network are connected at rest. Extracting time series from the ROIs. Identifying each of the ROIs within the DMN by extracting the average time series of activity from the corresponding voxels within these regions across the fMRI dataset. For each voxel in the ROI mask, retaining the corresponding bold signal intensity values from the fMRI data over time. These time series represent the average neural activity within each ROI over time, capturing fluctuations in the bold signal that correlate with neuronal activity. Detecting stochasticity in signals. Identifying stochasticity in fMRI time series involves recognizing patterns of variability that cannot be attributed solely to the neural processes of interest but rather arise from random or unpredictable sources. using statistical measures such as variance, standard deviation, and autocorrelation coefficients to assess the degree of variability in the fMRI time series. Random fluctuations not related to neural activity typically exhibit irregular patterns and lack consistent trends over time. Calculating deviation from stochasticity. Adopting an autoencoder-based time invariant representation for measuring deviation from stochasticity in fMRI time series. Dividing the time series signal into a number of windows and computing discrete Fourier transform, DFT, on each window to obtain spectral information. Calculating the deviation from stochasticity, DS metric, in the fMRI time series by computing the window-wise bias from the input time series signal. Adding this bias to the dissimilarity curve. Computing KL divergence between the input time series signal and bias-corrected dissimilarity curve, and calculating the coefficient of variation. Comparing DS metric between subjects and among ROIs. Comparing the DS values between healthy and affected individuals and observing consistent trends within each class. Comparing the DS values among different ROIs and observing variations in the DMN. Here is a combined summary of pages 7 and 8 of the research paper. The study investigates the variation in the deviation from stochasticity, DS, measure among paired regions of interest, ROIs, for each subject, revealing significant changes in DS values between symmetrical ROIs in both healthy control, HC, and Alzheimer's disease, AD, classes. This asymmetry helps identify the main regions deviating from stochasticity. An ablation study was conducted, computing coefficients of variation, CV1, CV2, for each of the 100 subjects, which showed significant differences between HC and AD subjects. The data was fed into various classifiers, with the support vector machine, SVM, and gradient boosting classifier, GBC, achieving accuracies of 95% and 85%, respectively, for covariance-based classification of subjects. A scatter plot was generated, distinguishing AD and HC subjects based on CV1 and CV2 values. Shapley additive explanations, SHAP, was applied to explain the internals of the classifier, assigning a value to each feature. The ROIs represented as features included anterior prefrontal cortex, inferior temporal cortex, and post-cingulate cortex, among others. The autoencoder-based deep learning model was applied to quantify the deviation from stochasticity for each subject, with the DS measure calculated for all subjects corresponding to the 34 ROIs. The values were given as input to classifiers, with the GBC achieving a high accuracy of 95%. The T-distributed stochastic neighbor embedding (TSNE) technique was applied, mapping high-dimensional data into a lower-dimensional space, and the receiver operating characteristic, ROC, an area under the curve, AUC, were plotted to evaluate the performance of the classification models. The SHAP technique was applied to assign each feature an importance value for a particular prediction, with the ROIs represented as features including interparietal sulcus, fusiform gyrus, and medial prefrontal cortex, among others. The study confirmed the nodes contributing to AD versus HC classification and plotted the DS values among the HC and AD groups corresponding to the ROIs, observing a consistent pattern in DS values in healthy controls and an abrupt pattern in the AD group. The study investigates the disparities in the DS measure, proving that there exists a variation in the stochastic behavior of time series associated with 4 cases. Within HC subjects, within AD subjects, among all subjects for a fixed ROI, and among the paired ROIs in the subjects. The results provide a good method to segregate the subjects based on the DS values. The research paper discusses the utilization of the deviation from stochasticity, DS, metric for identifying disparities in time points of fMRI data. This approach enables the classification of individuals into healthy controls and those affected by Alzheimer's disease, AD, based on the stochastic behavior of each region's time series. The DS metric is found to be a valuable biomarker for AD classification, offering a novel approach with high accuracy. The study incorporates machine learning models, such as random forest classifier, RFC, and gradient boosting classifier, GBC, to classify subjects with AD from healthy controls. The results demonstrate a high accuracy of 95% in classifying subjects using the DS metric, highlighting its potential for clinical applications. The paper also reviews various studies and methodologies related to fMRI data analysis, emphasizing the importance of understanding brain function in disorders.